hertz of our sound. A single alternation of our wave is called the period, and its measurement is the wavelength, which is also in feet or meters per second. The frequency is how many times the period repeats in 1 second, and this is measured in hertz. Longer wavelengths mean that our wave doesn't vibrate as many times in a second, so we have a lower frequency. Longer wavelengths equal lower frequencies, and lower frequencies give us lower pitch. And the smaller our wavelength is, the higher our frequency. So our frequency increases, and so does our pitch and the number of vibrations per second. Another thing that's very interesting, not only in sound, but just kind of physics in general, is that when we have equal and opposing forces, they basically just cancel each other out. So it's kind of like taking two people with the same strength and putting them in an arm wrestling competition together. Essentially, nobody wins. So if two waveforms collide, and they both have equal and opposing forces, that wave cancels out. So one quick example of how we're going to be using all of this information that we've learned is by calculating the distance that it takes for certain tones and frequencies to complete a full cycle. And again, you'll recall that that will be the period of our wave, which is measured by the wavelength. So let's take the tone of 100 hertz and figure out its wavelength. All we need to know is the speed of sound, which is going to be 1,126 feet per second, and then we divide that by our frequency, which is 100 hertz. That gives us a distance of 11.26 feet. So a sound wave at 100 hertz doesn't complete a full cycle until it reaches 11.26 feet. Now, this isn't too important to know at this moment, but we will be using this calculation later on in the series. It's actually going to help us make the best through gases, hold room temperature air and humidity, like that same stuff that you're breathing in your studio. So for this series, the speed of sound is going to be 1,126 feet per second, or 343.2 meters per second for our friends that are using the metric system. So just save that number because we'll need it for conversion in some of the upcoming chapters. So just write it down, put a sticky note on your desk, and refer to it later. Next, we're just going to refamiliarize ourselves with the waveform and the waveform display. A waveform display is just one of the ways that we can view some of the properties of a waveform and to make them easier to view and work with. And these waveform displays are the same things that you look at in your DAW software. So the up and down axis is going to refer to the amplitude of the wave or the intensity or strength, and the left and right axis is going to refer to time. By plotting the intensity of our wave at different points in time, and then connecting the dots, we get our waveform, which is just a basic representation of the vibrations in the air. Now, these vibrations have both a positive swing and a negative swing, with the center line representing what we call our zero crossing, or our resting point. Once a vibration occurs, this vibration alternates between the positive swing and the negative swing of our waveform display. These positive and negative swings we refer to as the phase of the wave. So one of the cool things that we can see from these waveform displays is the phase velocity, which is essentially the direction and the speed that our wave is moving in the display. And the best way to understand this is to take a closer look at our breathing patterns. As our waveform goes up, we're breathing in, the speed of the air that we're breathing in increases until our lungs are filled up. The speed slows until we're ready to exhale. The top point of the waveform is called a crest. Now, as we breathe out, I like to picture this as the waveform going down into the negative side of our waveform display. Once we fully exhaled, we reach the trough. So the speed of the air decreases as we reach the trough, and then reverse the direction of the air as we breathe in and reach the crest at the next positive swing in our waveform display. As we view this alternating pattern, we can start to come up with a few other visual representations of our sound. In this video, we'll be learning more about the source of where our audio comes from in the studio, and that's going to be our speakers. Since our speakers create our audio, it only makes sense to learn a little bit more about their behavior, take a closer look at how they work, and look at some of the best practices when using speakers in your home studio. We're going to cover some of the basics here and try to get you pointed in the right direction. One of the most important things to remember about speakers is that they're motors. These are motors that push around and vibrate air. So there are moving parts. There's a very physical and audible relationship with our immediate environment and our direct surroundings. Now think about your cell phone for a moment. When you receive a text message and your cell phone's sitting on the coffee table next to you, when your cell phone vibrates, so does the table. And it amplifies the sound. The energy from the vibration of the cell phone is transferred into the table. And also, in a similar way, the energy from our speakers may be directly transferred to whatever they're resting on. And this actually has quite a bit of impact on the sound that you're hearing, because you're not only hearing the sound from the speakers, but you're also hearing the sound from the object that's absorbing the speaker's vibrations. So one of the first steps that you can make that will automatically give you a better sound is through the process of what's called decoupling. When you decouple something, you're basically just preventing an object from making direct contact with another. More specifically, we use some type of shock-absorbing material, like foam or rubber, and put them between the two objects that we want to decouple. And this works typically because these materials are slightly elastic and can easily absorb and dissipate this energy before it passes through to the other object. Now, many of you may have your speakers resting on your desktop. In a scenario like this, the best choice would be to remove the speakers from the desk altogether and put them onto speaker stands. Well, sometimes in the home studio we have space constraints and budget constraints, so moving them onto stands may not be ideal. So the next best option would be to use a monitor isolation pad. On the low end of the budget, it's made out of dense foam, and on the high end we can see some crazy contraptions that suspend our speakers like a microphone shack mount. Hello everyone, welcome to Home Studio Know-How. My name is Dave Askew. As musicians and engineers, we spend an awful lot of our time and money, well, mainly